Hello. Jesus. Loud, isn't it? Good morning, everybody. I'm Sam. As I think you may have been told, but I don't know because I'm afraid I don't speak Chinese, I work for Raiseware, which is a really small company that is behind the world empire of RayWendeling.com. Ray sends his regards, by the way. He's on holiday at the moment, but he wishes he could be here, so you've got me instead. I spend most of my time now doing lots of website stuff, so I do lots of stuff in Ruby on Rails, I do bits of WordPress, but I do still get time to do iOS, and that's my primary love. So I'm going to come and talk to you today about iOS, about concurrency on iOS specifically. Now, this talk is like an hour and a half long, so we're not going to do the whole talk. What I'm going to do is work out which bits would be best for me to do for you guys. So I'm going to ask some questions at the beginning. I want you to bring your hand up. So if I start talking about things like race conditions and priority inversion and deadlock, does that make sense to you? Stick your hand up if you know what those things are and you understand it. So race conditions, priority inversion, all stuff to do with concurrency and multi-threading. No? Okay. In that case, that's great. I won't ask any more questions. I'm going to start then with a bit of a run through some of the theory of concurrency, and then we'll start looking at what you can do in iOS. And then there's a bit at the end that we won't even get to, but I might tell you about it, and you can look it up later. I want my real name on Twitter because there are far too many people in the world called SamDavies. Some people like professional yachts, women and things. That's not me. So I might want my real name. And you can get the code for what I'm going to be doing. I've got a bit of a playground that you can get there with that really easy to read URL. Little v, 9, big Q, 3, big F. Easy to read. And anyway, before we start, concurrency is really hard. I mean, that's it. Thank you very much, Mark. Concurrency is really hard. The reason it's really hard is because you can't determine exactly what's going to happen when. That's basically what it comes down to. Concurrency is the fact that you can do more than one thing at once on your device, whether it be a phone, whether it be a desktop, and has been true for about 40 or 50 years. And we implement things on top of that to make the you can do more than one thing at once much easier to understand. That makes it hard. So what exactly is it? In order for your device to kind of behave in a way that people would expect, you want a really good user experience, you've got to do more than one thing at once. You probably know that on an iOS device, the only place that you can update the screen is on the main thread, on the main queue. You can't do it anywhere else. But you've got to keep 60 frames per second. You have to refresh the screen every 60 frames, every 60th of a second, because otherwise it'll look like it's dragging, it's slow. But what if you've got a big job to do that takes longer than the 60th of a second? I've got to download stuff from the network, I've got to filter this big image, I've got to process this video. I can't do that on the main thread, I need to do that as well in the background. And threading, concurrency, is what allows you to do that. Oh, I've just answered that question. Why use it? Because of what I just said. So now I'm going to talk about some common concurrency problems. There's those things that I mentioned before. I'm going to start off with a race condition. So what is a race condition? Those of you with a computer science background probably know all of this, but I think it's quite helpful just to revise what is the point of doing all of this concurrency and when can it go wrong. So a race condition, what we've got here is, along this axis here is time. So time is ticking along, and then we've got two threads. So two threads that can happen at the same time. And at the top is some kind of memory value. It's got a value of 1 at the moment. Thread 1 comes along and says, I want to increment that 1. So I want to add 1 to the value in memory. So what does it do? This is the next clock tick, the next cycle, the next thing that the processor does, is it reads that value 1. And then it's going to add 1 to it. So 1 add 1 will be 2, and then it will write that 2 back to memory. Then thread 2 comes along and says, I also want to increment that value in memory. So what does it do? It reads in 2, it adds 1, and writes it back. So you've got 3. We started out with 1, we added 1 to it twice, we've got 3. 1 add 1 add 1 is 3. Brilliant. No problem at all, that's perfect. Let's imagine another situation. Thread 1 comes in and wants to increment that value 1. So it reads 1. Then thread 2 comes in and it also wants to increment that value with 1. But thread 2, for some reason, and this is where it gets difficult, because the operating system gets to choose, well, it's this thread's turn now. And you can put some things in there saying that this thread is more important than this thread, or this one is less important. But essentially, as a programmer, you don't have much control over this. The operating system decides, actually, thread 2 is more important, we're going to do that now. So that reads 1 in, then it adds 1 to it, and writes back 2. So now the value is 2. Now that thread 2 is finished, thread 1 can start again. And it's already read the value, so all it needs to do is add 1 to it. And then it writes back 2. So what we've got now is we read in 1, we add 1 to it, we add another 1 to it, get 2. 1 add 1 is 2. It's not right. That is basically a race condition. It's to do with the fact that 2 different threads, depending on various different timing circumstances, can do completely different things. And you end up with inconsistent memory. That is one of the major issues that you have with concurrency. 2 things happening at the same time can really screw you over. Next one then, priority inversion. This is another joyful thing that is really difficult to get your head around and program around. Remember I said that different jobs, different threads, different tasks can have different priorities? Well, that's exactly what's happening here. We've got a resource, so you can think of memory or maybe a network access or some kind of thing that only one thing can use at once. And in order to get around the idea of race conditions, when a thread wants to use it, it can lock that resource and nothing else is allowed to use it, which is a fairly standard way to deal with race conditions. So a low priority task comes in and it's doing some work and it says, I need to use this resource, I need to use this bit of memory. So it locks the resource. Nothing else can use it now. But that's fine, it keeps going. Then a medium priority task comes in and then the thread scheduler says, okay, this one's more important than the low priority, so I'm going to stop the low one for a minute and start the medium one. But the low one still has a lock on the resource, which is also, that's fine. Then a high priority task comes in. That stops the medium one, which is stopping the low one. The high one starts, and then it requests a lock on the resource, which it can't have, because the low priority task has locked that resource. So the high priority task stops, can't do anything, and then it allows the medium priority task to carry on. And this point here is priority inversion, because what you've got is a medium priority task running when there's a high priority task that should be run, that is more important, that isn't allowed to run at the time. The priority of those 2 tasks has become inverted. And what eventually the way that this will play out, depending on the thread scheduler that you've got, the medium priority task will continue until it's finished, and then the low priority task will be allowed to run until it releases the lock, at which point the high priority can carry on, and then once that's finished, the low one will be allowed to run. Now, the weird thing about, the reason this is kind of important is that I think it's quite a useful example. This actually happened in a fairly major piece of software. I don't know when it was, I can't remember, but the Mars Pathfinder mission sent a rover off to Mars, and within it, they got something that did exactly this. They had some kind of low priority task that started when they first started booting, and it locked something like a communication system. Then we had some stuff going on, and at some point here, the medium priority task was running while the high priority task was frozen. The high priority task was something like communicating back to Earth, some such thing. And the problem with this was, they put something on the top of this to say, if this high priority task is frozen for longer than a certain amount of time, something's gone wrong, so reboot. So it went through, this high priority task was frozen, and it rebooted. It started back over here, and did exactly the same again, and it went backwards and forwards, round and round and round. Now, if you think debugging in Xcode is hard, You try debugging something that's on Mars, because I think that's significantly more difficult, right? They've got to debug this thing, rewrite the code on something that takes 15 minutes to communicate. There's a really interesting write-up somewhere on Microsoft that explains exactly how this happened and what they did to fix it. Anyway, on to the third concurrency nightmare we're talking about, and that's deadlock. So I just spilled the dead and have a deadlock, quite proud of that. What is deadlock? With the same kind of graph again, we've got two resources this time and two threads. Deadlock happens when two things or more become locked against the same thing. So thread 2, thread 1 requests a lock on resource 1, it gets it. Thread 2 requests a lock on resource 2, it gets it. They carry on happy. Then thread 1 wants a lock on resource 2, which you can't have because thread 2's got it. So it pauses, and thread 2 continues. Until the point that thread 2 then says, I want a lock on resource 1, which it can't have, because it's waiting on thread 1 to release that lock, which is relating on thread 2 to release the lock on resource 2, etc., etc. And you end up with this point where neither of these things can ever finish, because they're both waiting on each other to release a lock on the thing that they're locked. So another challenge with concurrency. Now, switching gears slightly, the way that Apple's frameworks deal with concurrency is not. You can use threads, you can absolutely use threads, but there's quite a nice abstraction on top of that based on queues instead of threads. Here's a queue, there's some people in a queue, this is a queue. So the idea of a queue is that I break down what I want to do into like small little pieces of work, whether they be, and there's two different, you can either do this in Grand Central Dispatch, GCD and Dispatch, or you can do it in Foundations, called Operations, NS Operations, Operation Queues. Both use exactly the same principle. I break my work down into little tasks, I add it to the queue, and the system goes off and works out what threads to actually go. It doesn't solve all of those problems that we had before, but it does make it a lot easier. You're no longer responsible for managing how many threads have I got, how big is the thread pool, which thread should this piece of work go on. All of that stuff is abstracted away, and you end up with, here's a piece of work, go off and do it, and the queue will handle that. So what happens is you give it these pieces of work, and then the system will just choose, I'm going to put them on these different threads until they run. And the cool thing about that is that within a mobile device, where you have limited battery life, limited resources, then the number of threads available is dynamic according to the conditions to do with energy. If you're plugged into a wall and you've got loads of battery, it'll use loads of threads. But at the point that you are running low on battery, you make a battery saver mode on whatever it's called, then it'll start to ramp down the number of threads that it's using. Okay, at this point, we've all got a bit of an understanding of what's going on in the world of concurrency. I'm going to jump into a playground and take a look through some stuff. How many people have used or are aware of NS operation and operation queues? Have you got any idea on those things? Operations and operation queues? Okay, cool. Well, we'll talk about that first, and then we'll talk about Grand Central Dispatch afterwards. That's not big enough, is it? Can you kind of read that? It's going to be a challenge to type in here. Right. Let's move you out of the way. Okay, so remember I said that on a queue, then you package up little bits and pieces as a piece of work, and then you pass it up to the queue. Now, NS operation, or as it's now known as Swift operation, is something that exists inside Foundation that does exactly that for you. It provides the queue and all that kind of stuff. So imagine for a second that I've got this function here that I've called tilt shift. It's basically an image filter, but it's quite a slow image filter. It's artificially slow. Why can't I move you? I can't move that. Never mind. Which means that we can't see any of the answers. Right, so what I've got here is some code that is literally just running this tilt shift, function. This duration thing is a tiny little thing that I've done so that we can time it. So we can see how long it takes. It's about 1 second. It's particularly slow. And then the output looks something like that. It's a fairly crappy attempt at making a tilt shift version of this. So that's all that does. Now the idea of operations, ZS operations, is I can wrap that piece of functionality up in an object, like a command, like using the command pattern, I guess, if you're that way inclined. And the easiest way to do that probably is to use this subclass of operations called block operation. And with that, all you do is pass in a block, or a closure, as we call it in Swift, that actually does the work that you want it to do. So this one here, my first operation, is a block operation, and all it does is exactly the same as I did at the top there. And then to actually run it, then I call this start method. And then out here, you can see that the output image is the same as the output image that I had before. Now this is quite handy if you just need to throw something together, but it's not particularly useful. The more standard way of using operations is to subclass operation and override the main function. The main function is the thing that actually does the work. So we have here a tilt shift operation, subclass of operation. I've added a couple of properties to input and output images, and just overridden main with exactly that same function called again. And then I can create an instance of this, supply the input image, and then once again call start. And once that's finished, then you can see that the correct output has appeared in the output image. Now the advantage of that is that I can then reuse that same class for lots and lots of different images. However, what is the point of me creating one of these things, assigning image, and then calling start? There was no point. I could have just called the function. So that's where a queue comes in, an operation queue. The idea is, like we saw in the diagram, I create some of these tasks, and I chuck them in a queue, and then they get done for me. I don't have to consider when they get done. I don't have to consider which threads they go on. It'll just handle that for me. So say here, I've now got 4 different pictures that I want to filter in the same way. So all I'm going to do is, I've got exactly the same tilt shift definition, exactly the same operation. You create a queue using the default constructor, operation queue, and then you use the add operation method on an operation queue to add each operation to the queue. Now the important point here, if I run this now, is that adding things to the queue, which is all we're doing here, is we're going down each image, we're creating the operation, and then adding that operation to the queue. The important thing is that actually adding those things to the queue is really quick, right? It takes 0.9 of a second. I mean, that's not really quick, but it would be quick if my computer wasn't rubbish. Now, alright, and then what I've got further down here is this, how long does it take to actually complete all of those jobs inside the queue, which is what this wait until all operations are finished, which you wouldn't normally use. You would have some other way of getting the results out of the queue. But here I just want to see how long it takes. And you can see it takes 1.2 seconds, and we've got 4 output images down here. So we've got the original one, I've got some pictures of trains. I seem to take a lot of pictures of trains. Anyway, the interesting thing here is that we've managed to do 4 images in about the time that it took to do 1, and that's because an operation queue is concurrent by default. It does all of these things at the same time by default. But what I can do is turn it into a serial queue, this max concurrent operation count property. If I change that, to change it at the right time, if I change it up here, if I make max concurrent operation count 1, then that means you're only allowed to do one thing at once. You become a serial queue. If I run it again, the duration of adding the things to the queue is roughly the same. But down here, the duration to run all of those things in the queue is now about 4 seconds. Which kind of makes sense, right? It doesn't take any longer to add things to the queue, but the queue's only allowed to do one thing at once. Now, serial queues can be quite useful, and when we get to GCD, let's have a sponge, we'll see that serial queues can be used for all kinds of different things. Okay, so what I've spoken about here is operations. You override the main function to do the work. What happens if the work that I've got to do is asynchronous? So like if you made a network call, then quite often you'll write a function, you'll use a function that says go and request this thing, and then call this function, my handler, my callback, when you've got it. That's an asynchronous function, very standard asynchronous function. I send something and then I give you another function to call once you've done what you're doing. Well, I can't do that with an operation, right? Because the main function, as soon as that's finished running, we assume that the operation is done. Well, that's not true with an asynchronous function. Now, operations do support asynchronous functions. It's a bit of a pain to get them to work. I don't really understand, maybe somebody will be able to tell me, I don't really understand why this isn't something provided by Apple, but we can do it ourselves. All an operation is, all an operation has some different properties which specify whether the operation is ready to start processing, whether it's mid-execution or whether it's finished. And that's all that a queue uses. It uses those properties to work out, is this still working, is it not working? We can subclass operation to make an asynchronous version, i.e. one that you can map, one that you can use an asynchronous function in. To do that, I'm not going to go into any great detail, but basically it needs to support KVO because it's from old school Foundation, from like 20 years ago or something. So what I've got here is a subclass that does that. It has this enum called state, which has ready, executing, and finished, which all it does is make sure that it keeps those properties on operation nice and happy. And it does that with some KVO magic here. And then down here we override each of those properties to make sure that they respect the new state property that I've added. And then the start function, I override that as well to keep that state property up to date, and the cancel function as well. And what that means is, after all that stuff, which you can go and look at, this playground does explain roughly what's going on there, but once we've done all that, then I can create my own subclass of async operations for image load. So I have a function, whose name I can't remember, but I'll tell you in a minute, that asynchronously pretends to load data off the network. It doesn't actually load data off the network because this is a presentation and the network never works for presentations. So it simulates a network load. And what I'm going to do is wrap that in this async operation subclass that I've got. I'm going to try and do this. I'm going to put this down for a second, really loudly. There we go. Hello. So I'm going to override this main function. I'm going to stick a duration thing in there because I quite like the duration. I'm going to simulate async network image load. I'm going to call it takes the input name, so which is a string on this class, and then its callback. I don't like that. Right, so all I've done there is I've called this asynchronous network load image function that I've created, and I've given it the input name. And then its callback method, once it has loaded it, then it sets the output image to the image. And then the really important thing with this async network, operation subclass that I've got is that you set the state as finished. And once I've done that, then I can use that in exactly the same way as you would as in any other operation. I create an operation queue, I add something to it, and you'll see, well, I mean, you won't see very much because all it's doing is loading an image from disk, but you can see the output looks like an image that I've loaded from disk, so not particularly amazing. Moving on, I want to talk about operation dependencies, and I think this is one of the cool things about this operation, is that you can chain dependencies, you can chain these operations together and say, only start this one once I've got the results from this one. And I think that's one of the most powerful parts of operations. So, for example, in the one that I'm doing a lot of stuff here with images, then I can say, I want you to retrieve this image from the network, and then I want you to load that image, and then I want you to filter that image, and then I want you to display that image. So I can do that as like 4 operations, link them all together by saying, these are dependencies of each other, and then it will get on with it. So the way that we do that, although that I've done it here, is with a bit more code, which I think I'm just going to load from Git, because otherwise we'll be here all day watching me type. Which is here. So let's discard you and load you. So, yes, there we go. Right. So I've got another image, no, wrong one. That's the same image load operation as before, but I've now got this tilt shift operation here. And it's almost exactly the same. It's got an input image and an output image, and then the important part of it is the same again. Look, it's just doing tilt shift image, setting the output to the output of that filter. This bit up here, though, is a little bit different. And if I can drop down a little bit, I can explain. I've got a protocol called filter data provider, which all it means is that this thing that adopts this protocol can provide an image that will work as the input to a filter. So all it has is it has the ability to read a UI image called output image. And because I've already got that on image load operation, to declare conformance, all I have to do is declare conformance. I don't actually need to create that property. And then up here, in this little bit of swiftly code here, there is a dependencies array on operation, which is a list of all of the operations that this current operation is dependent on. So I'm going to go through those, and I'm going to find only the ones that are filter data providers, i.e. they adopt that protocol. I'm going to take the first one of those because of the ordering of it. I want the most recent one. And if I've got that, this line here just says if input image hasn't already been set, so just check that that's the case. Then all I'm doing is extracting the input image from my dependency image provider's output image. So the thing loads it. Once that's loaded, then the next operation can start, and it goes off and finds the result of the previous one as its input. And then one other thing that I've got in here that I'm usually quite hesitant over using custom operators because I think they can be quite confusing and make your code sometimes more difficult to understand. But in this case, I've decided that's a bit of an exception. And if I show you what I would have to write, because now that I've created this, I go and create those 2 operations, I set the input on the first one, and then I have to say that the filter operation has a dependency on the image load operation, which I find a little bit confusing. Which one is the dependency and which one is the dependent? Which one depends on which one? I find this a bit complicated. So I like to define this custom operator, which I'm not going to go through how to do that. There are people who are far more intelligent than me can show you how to do that. But what that means is that I can use this custom pipe operator thing that basically says that once you've got the result from image load, then it can pass on to filter. It does that through adding dependencies. Now once I've done that, I add those 2 operations to a queue, and I run that, and what will happen now is it's going to load, the first operation will run, load it from disk, then the filter will run, and I'll end up with an output of my filter that looks exactly the same as all of the other ones that I've done. And we've done that with 2 operations with this dependency. Now the dependencies, there I only gave one operation as a dependency of another. You can build up a whole complex graph of dependencies should you wish to. And the system handles which ones can run when. Now, operations in practice, I'm not going to go into this, but basically what I've got here is a demonstration of how you can use all of this together to make a UI table view kind of scroll quite nicely. That's the classic demonstration of when concurrency works really well. Don't try and load an image from a network at the point you're displaying the cell. So there's some stuff in here that does exactly that. We have a load operation, a filter operation, and an output operation. See here we've got the same kind of dependency chaining stuff going on. And then I've got a simple implementation of a data source or a table view. The only thing worth mentioning is something that was new in iOS 10, is this UI table view data source prefetching, which is quite cool. So at that point there, the table view will call this protocol, this delegate, and say, in a few seconds now, in some amount of time soon, I'm going to want to display this cell. So if you want to go off and start downloading that data, that'd be really handy. So that just gives you a bit more of a heads up as to when something's coming in. And it also tells you, actually, I don't need to prefetch that anymore with this cancel prefetching. Those two things together are really handy for improving performance. But at the same time, the idea of being able to cancel a long-running operation is exactly the kind of thing that operation queues are really good at. Okay, so that's the end of my kind of quick summary of operations. I don't know what time I'm supposed to finish. I'm going to keep talking until somebody drags me off the side of the stage. Talk about Grand Central Dispatch. So, operations, as I said, are in the foundation. They've existed for 20 years or so. You can use them in Objective-C, you can use them in Swift. They're all quite nice to use in some senses. But they do rely on KVO and some kind of fairly old school techniques. They are built on top of something called Grand Central Dispatch. That's the marketing name. We can live dispatch. I guess we don't need to be marketed to. And it uses exactly the same paradigm of queues and bits of work. And this is almost certainly what, when you've done anything in iOS that involves concurrency, you have used GCD in some sense. And if only when you're writing your first app and you can't work out why isn't this appearing on the screen, and then you go on to, well, I would go on to StuQ Overflow. I don't know whether, do you guys use StuQ Overflow? Yeah? And you would go on there and it would say, well, what you need to do is make sure that you're doing rendering on the main thread, copy and paste this bit of code and work. We've all gone there to StuQ Overflow, copied that bit of code, pasted it, and then it magically works. You've probably done that with libdispatch with GCD. I'm not going to go too much detail about building queues and running stuff on them because I think this is stuff that you probably already know. But the idea is the same kind of thing again. You create a queue and you push bits of work onto that queue. You can specify different quality of service classes. So remember before I was talking about priorities? A slight abstraction away from priorities is this idea of quality of service. So you can say whether it's user initiated, whether it's updating the UI, whether it's just a background process. The system uses those to work out how important this is. Should it be running now? I haven't got much battery left. I'm not going to do any background processes or some such thing. If you want to send off some work asynchronously, so that means this function will return straight away, and at some point in the future, your code will run. Then you can use, you build a queue and then you call .async on it, and you send your work off on there. And similarly with synchronously, that means that this current call cycle will block until that piece of work is completed, then you use the sync. Remember that I said that NS operation queues are by default concurrent, i.e. lots of things happen on them at the same time. GCD queues, by default, are serial. One thing happens on them at once. But you can have concurrent GCD queues in the same way as you can have serial NS operation queues. And to do that, there's you specify the concurrent attribute when you're building a queue. It's that simple. Now I'm going to talk about a couple of things within GCD that I think are quite cool, quite useful, that you may not have seen. The first one is GCD groups. The idea of a group is saying, well, I've sent all of these 5 different things off to GCD queue to process, to go and do this bits of work. When do they finish? I want to know when all 5 of those are finished. I don't care that 1 and 2 are finished. I want to know how all of them are finished. And you can do that using a dispatch group. And I think these are quite cool. And the example I'm going to give is using animate with duration. So if you imagine I've got 3 animations that I want to run at the same time, and I want to know, tell me when all of those animations are finished. Well, I can do that by creating a new function, so animate, using one of the UI view animate functions, the animate with duration, animations, and completion. I'm going to wrap that in a new static function called animate with duration, animations, this time adding a dispatch group and completion. And all I have to do is, as I start the work, I enter the group, and as I finish, I leave the group. And all that a group really is a number, and it increments that number when something enters a group, and it decrements it when something leaves the group. You can implement this yourself, but this is nice, easy, thread safe, and well supported. So that's all I've got here is I've created a new function for animations that adds a dispatch group. And then I can go ahead and use it. So I've got some setup code here that builds an animation with you. And we've got this code here. We're going to animate the center of a box. We're then going to animate something else. We're going to rotate it. We're going to animate the color. One of those things is going to happen when the first one's finished. The other one's happening kind of simultaneously. To work out when all of that finishes without dispatch groups would be quite hard. But if I switch these with duration animations functions to using a group as well, so if I add my group, which I think I've called animation group, yeah I have. So I'm going to grab these and paste them in, where is it? After here. So we go you there, and we go you there. So all I've done is replaced the original UI kit functions with my own one that adds a group. I create a group. Where did I do that? I created a group here, just by doing animation group is dispatch group. And then, let's see if we can get this to work. So hopefully, you'll see an animation on the right-hand side, and then somewhere down the bottom in this thing here, it'll tell us when all the animations are completed. Is it going to work? Yes, there we go. There's an animation. And once all of those things are done, it tells me that the animations are completed. So that's a dispatch group, right? And that allows me to take several different GCC things and tell me when they're done. You can link all of these things together really loosely through a dispatch group. Okay, I think probably the last thing I'm going to talk about is making something thread safe using dispatch barriers. And for that, I need to go back to some pictures, a bit more theory. So we're back to one of our familiar diagrams. We've got time on the bottom, and we've got 3 threads now, and some kind of memory that has more logic at the moment. And what we're going to do is change that memory. I can't remember how we're going to change it. Oh, I see, right. So thread 1 is going to read 11111. And then thread 2 is that I want to write to that memory 2222. Now, if you imagine that this is clock cycles, writing takes 4 clock cycles, reading takes 1. Arbitrarily, I mean, some of these things are true once they're onto some kind of silicon, but this example here, the principle is exactly the same. So, the first cycle of writing 2222, it manages to change just the rightmost, the least significant, not a bit, couldn't be a bit, digit. And then thread 1 comes along and it reads it, and now it's reading 1122. But it should never be 1122. It should either be 1111 or it should be 2222. This 1122 thing is now inconsistent state. And then thread 1 goes along and tries to write 3333. Thread 3 reads it, and we've now got 1223. It's just a complete inconsistent mess. And this continues. Eventually, in this particular case, we will get consistency right down here at the end. It will end up with reading 3333. But throughout this entire period here, while you've been reading, we get completely inconsistent results. And that's because this memory is not thread safe. You can get around that by putting a lock on that bit of memory, so you say who's allowed to read it and who's allowed to write it. But in the queuing paradigm, there are different ways to deal with it. And that here is through using a barrier task. So the idea of a barrier task is, I've got this concurrent queue, and I can do all of these blue tasks. It doesn't matter that they're happening at the same time. That's absolutely fine. But then I have this special type of task called a barrier task, which says nothing else is about to happen whilst this task is going on. I basically turn the concurrent queue into a serial queue for the duration of that task. Nothing else can work on that queue at all. So how does that apply to the thread safety memory access? Well, all of these things that can happen at the same time are read operations, read tasks. And the barrier task becomes a write task. So whilst this one is writing, nothing is allowed to read from it. But when something's reading, it doesn't matter. You can do multiple things to read from the same memory at once. That's fine. So, back to some code. So I've got a person class, which I've deliberately made obviously non-thread safe. It basically has a first name and last name. It's all a person has, apparently. And on there it has a method called change name, and it has a property, a computer property, which combines the first name and last name. So what I'm doing here, in this somewhat overcomplicated code, is I'm taking this person class and I'm going to change their name repeatedly. And the important thing to notice is that every name that I give them, the first name has the same start letter as the last name. And if I run that, what happens? If I can find the run, here it is. If I run that, then I need here. Then you can see this bit here, this is the important bit, which is a bit small. Let's move it up a bit. Then the only name there that is consistent is Eva Evershed. I think it's the only name that has the first name and last name beginning with the same letter. All of those other ones in that first bit are completely inconsistent. And that's because it's not thread safe. What we're doing is changing the name at the same time from multiple different queues. But we can change that, and we can, where it says thread safe, we can actually make it thread safe. And we do that using a dispatch barrier, like I said. And I think I'm probably running out of time, so I'm going to again jump and grab it from Git, because I'm lazy. Here we go, thread safety. So that to-do should change. So here I've got a subclass of the person class called threadSafePerson. Inside that class I've created a dispatch queue. It's a concurrent queue because I want to be able to read multiple times. So I've called that an isolation queue. And I've overridden two things. I've overridden the change name method, which takes first name and last name, and I've overridden the name property, the computer property for name. What we do is, when we change a name, then I'm going to give you a first name and last name. I'm going to send that asynchronously onto the isolation queue, but I'm going to specify that it should be a barrier task. That's what that flag barrier means, is that I'm passing on to that queue a task that should be treated as a barrier task. Nothing else can happen whilst that task is in progress. And I'm just going to pass that up to the superclass, which can handle changing the name. So we call super change name in the first name and last name. But that piece of work can't happen at the same time as anything else. The other thing we need to do is make sure that when we read that property back, that also happens on that isolation queue. If it happened elsewhere, then we wouldn't be making it thread safe. We have to put it onto the same queue. And this time here is a little bit different. We need to, because this property returns something, we've got to dispatch it synchronously, because I actually want to return a value. So here, on the isolation queue, we synchronously dispatch just to tell me what it is in the superclass. And now if I run that again, then hopefully it will have worked. Yeah. Right, so now you can see that the thread state names are always consistent. There's always Charlie G, there's always C, C, D, D, E, E, F, F, G, G. It doesn't mean that at any time that I guarantee that I've got a particular name, but I can guarantee that that person object is always consistent. And using GCD queues is quite a nice way to guarantee thread safety in that way. Okay, I'm going to talk very, very briefly about alternatives. but I'm not. I've got some code in there which I'm not going to show you because I think I've talked too long. You haven't talked at all. So alternatives to Apple. This is kind of some pseudo GCD code where I'm going to make a request, I'm going to decompress something, I'm going to resize it, I'm going to filter it, and I'm going to display it. And what you notice is that this ends up in this kind of pyramidal, that's a word I'm going to use before, and like this pyramid kind of shape going across the page. The more things that you nest, the more difficult it gets. And then it gets even more difficult because I've ignored the fact that any of these can have a problem. You would normally have error handling in there as well. This was a massive problem in JavaScript as well, for those of you who are in the world of JavaScript. This kind of callback thing is exactly the way that JavaScript works. With a callback for it works and a callback for it fails. And you end up with this really complicated pyramid of doom. So what a promise is, you may have heard it called a future, it's basically this kind of type that at any stage it can either be a success, which it usually is generic over the type, so this promise of an integer, it'll either be an integer or it'll be an error. That's all it is, it's just an enum that wraps that basically. And then, so we get in and we start off with the string, and then there's some kind of function that takes that string and returns a promise of an image. That means that this isn't an image now, but at some point in the future, I will be able to give you an image, or I will have had an error. If I've had an error, then I can send it off to an error handler there. But the result of that, I can pass on to another function, which takes an image, or a promise of an image, and processes that. And that will also return a promise of an image. It will either return an image at some point in the future, or it will return an error. And the cool thing about this is that that error, I can send to the same error handler, because everything just runs along here. We handle the errors at the end. You haven't got that pyramid of errors. So that pyramid that you saw before, then becomes this kind of pipeline. You start out with a network request, and then you send it to a decompressor, then you send it to a resizer, then we've got something here that's going to filter it, then we display it, and then we catch right at the bottom. If any of those things had an error, then we catch that error at the end. Now there are various third-party frameworks that you can use to handle promises and futures, and this kind of thing. It's quite nice, I think, in some senses. I said I wouldn't show you the code. I'm going to show you a really simple implementation of futures, and I'm not going to talk about it. But I want to show you this here is a incredibly naive and simple implementation of a future. It's not really that complicated. If you then go off into the third-party frameworks, you add a lot of extra functionality and stuff, it will be a lot more complicated and a lot more fully featured, and it would actually work. This is a bit of a mess. But fundamentally, it's not that difficult to build something like this and then chain these things together. And so, for example, here, this is what the code used to look like, and then if I use my mini future thing up there, then you can turn it into something that looks like that, which is a lot easier to comprehend and a lot easier to handle the errors. That, as I said, is all the code that's available in the GitHub repo, so you can take a look at that. Now, one final thing that I want to briefly mention, which will hopefully fit quite nicely with the talk that you'll see later today. Imagine the promise pipeline accepted a sequence of values. So we've got this pipeline of functions that says, in the example I had, take a string and turn it into an image, take that image and resize it, turn it into an image, take that image and filter it, take that image and display it. But you're going to use that once. You build this thing and then you use that thing once. But imagine if it accepted a sequence of values. I'm just going to keep chucking strings at you and I want you to return me filtered, resized images. Or that thing that I'm chucking stuff at you, it couldn't be strings, it could be clicks on the screen, it could be taps on the screen, it could be keyboard input, all of that kind of stuff. Where rather than sending one thing once, we have a stream of stuff going through. That's basically hand-wavy, really kind of not talking in any specifics, basically reactive programming. So if you understand promises, reactive programming is not too far away from that. Promises are, in my mind, a special case of reactive programming, and with things like RxThread or reactive Cocoa. So, And with that, I think I must be way over time, for that I apologise greatly. I should jump into a little conclusion. The concurrency is really hard. You'll get it wrong. Thank you very much.